If you're running your Kubernetes clusters via GitOps, which you absolutely should by the way, well, then you've probably got the stateless side all figured out. Your manifests are stored in Git, then Flux or Argo if you're one of those, you then reconcile them, everything's declarative, life is good. But at some point you're going to look at your PVCs and realize that that data isn't in Git. And if that volume disappears, well, no amount of state reconciliation is bringing it back. Let's fix that. Hey everyone, Mircea here. In my last video, I walked you through how I use Flux to manage my cluster with GitOps. One of the things that I briefly mentioned was that I use VolSync to handle persistent data backups and, more importantly, automated restores. A few of you asked me to go deeper on that, so here we are. In this video, I'm going to break down what VolSync is. We're going to talk a bit about how it works under the hood and how I'm using it in my home production environment. I'll show you a nice hack via reusable customized components that makes adding backups to any app a 2-line change or so. We're going to look at some Taskfile automation to make the occasional manual operations a breeze. And finally, we'll do a full demo where we deploy an app, back it up, nuke it from orbit, and then watch all of the data come back. To quote the official documentation, VolSync is a Kubernetes operator that performs asynchronous replication of persistent volumes within or across clusters. Let's unpack that for a moment. First of all, being an operator, we can already assume that it will be one or more controllers managing one or more CRDs. Generally speaking, operators bring in their own custom resources to extend the Kubernetes API with extra functionality, and then custom controllers to operate upon those resources. The keyword in this official documentation is asynchronous. This is not real-time mirroring like you'd get from a distributed storage system such as Ceph. Video right here. It's scheduled point-in-time copies of your PVCs shipped somewhere. If you've watched my TrueNAS backups video, the mental model is similar to what ZFS does with snapshots and replications. You take a snapshot of your data at a given point in time, you send it somewhere off cluster, and if things go sideways on the original location, you can always pull it back and restore it. Kubernetes by itself has no built-in mechanism for backing up the actual data on your persistent volumes. You can back up your manifests and your cluster state, and tools like Velero can help with that, but the actual bytes sitting on your disks, well, those are on you. And VolSync fills in that gap by giving us a declarative, CRD-based way to handle both the backup and the restore tasks. If you look here in my cluster, you can see in the storage system namespace, I already have VolSync up and running right next to my OpenEBS ZFS CSI and my snapshot controller. I'm name dropping those since they will be relevant in a bit. I won't go into much detail about the deployment manifests since those are fairly basic Helm installs. You can find the Flux custom resources in my Git repository, linked in the description if you want to take a look at them. If we navigate to the CRDs tab and filter for VolSync, you can see that it introduces two main custom resources. A replication source, which is kind of the equivalent of a backup or send data from this cluster, and the replication destination, which is the equivalent of a restore or fetch data into the cluster. Let's start off with the replication source because that's where the backup story begins, and these are all of the replication sources running in my cluster. Let's take a look at the Jellyfin one for an example. You can see right here that the specs section marks a single source PVC to be backed up, and this would be the Jellyfin PVC. If I open up a new Zellige tab and go into K9S again, and then I navigate to my media namespace, here I can check all of the PVCs and filter for Jellyfin again. This is the Jellyfin PVC that VolSync will back up, and this replication source is essentially a CRD or a manifest that tells VolSync when, what, where, and how to back it up. This covers what? I want to back up this PVC right here. When do I want to back it up? Well, that is where the trigger schedule comes in. This is just a cron syntax that tells VolSync how often I want my backups to run, and in my case, that's every 2 hours. The trigger also supports a manual field, which I'll come back to later when we talk about the Taskfile automation. That covers the what, so the PVC, and the when with the trigger. For the how, VolSync supports several different movers, essentially the backend tools that handle the actual data transfer. There's rsync and rsync TLS for direct cluster-to-cluster replication, syncthing for continuous file syncing, and you have rclone for, well, rclone-based transfers. However, in this video, I'm focused on using VolSync as a backup tool, backing up PVC data to object storage and restoring it when needed. For that use case, the Restic mover is the natural fit, and that is what I'm running, so everything from here on out is going to be Restic specific. You can see here in the replication source, there's an entire Restic section, and this basically tells VolSync what the repository is by referencing a secret. And if I go here into secrets and again filter for Jellyfin, you should be able to see this Jellyfin VolSync secret. This contains the AWS access key ID and secret access key, which are essentially the AWS S3 credentials to authenticate against the S3 endpoint. We have the Restic password because you can encrypt your backups before they even reach the S3 endpoint, and this is particularly useful in case you're backing up to public providers like Backblaze or AWS. Then you also have the Restic repository, which is just the S3 endpoint, the bucket and the path within the bucket where you want your backups to land. This covers the where part, so we know what we want, the source PVC, when with the trigger, and where we want to ship it to this repository right here. There are a few more fields which I want to cover, specifically this copyMethod right here. This is an important one because it defines how VolSync gets a point-in-time copy of your data before backing it up. There are three main options. We have snapshot, so VolSync asks your CSI driver to take a volume snapshot of the PVC. Then it creates a temporary volume from that snapshot. This is what I use, and it requires that your storage backend is able to support CSI snapshots. However, it also means that the backups read from a frozen copy while your application keeps running against the live volume, so your app never sees any interruption. Then you also have clone as an option. It's a similar idea, but instead of taking a snapshot and restoring it, VolSync clones the PVC directly. Some CSI drivers support cloning but not snapshots, so this is an alternative. The end result is the same. You have a point-in-time copy that the mover pod reads from. Then you also have direct, and this means that there's no point-in-time copy at all. The mover reads the data live from the PVC. And while this sounds simpler, it means that either your app needs to not be writing to the volume at the time of the backup, or you need to accept that the backup might be inconsistent. Once you start shipping backups, you might want to set a retain policy on them, and that is where this configuration comes in handy. Basically, this tells Restic how many snapshots you want to keep across different time buckets. You can see here, I keep 1 day worth of hourly backups and then 1 week worth of daily backups. Restic actually has a two-step cleanup process. First, it forgets snapshots that fall outside the retention policy, but it doesn't actually delete them. It just marks them like to be deleted. Then it needs to run pruning on the repository to actually reclaim the disk space from the forgotten snapshots. Pruning is more expensive than forgetting, so you don't want to do it on every single backup run. That is where the prune interval days configuration comes in, and I have it set up to 2 weeks. On top of that, we also have configuration for a cache volume, and that is because Restic maintains a local metadata cache to speed up operations. It is used to avoid re-downloading the repository metadata from S3 on every single run. VolSync creates a dedicated PVC for this cache, which you can see right here. Again, if I go into PVCs and filter for Jellyfin, it's this one. It does need to persist between backup runs though, but if it gets deleted, Restic will just rebuild it from the remote repository, so it's not catastrophic, it will just be slower. One mention here is that you can see my cache capacity is set to 5 gigs, and I guess you can call this technical debt from my initial implementation. The default, I believe, is 1 gig, and you don't really need that much storage for the cache volume. I should probably revert back to that one. The last important section here is this mover security context. Now, what happens is that when you run a backup or even a restore for that matter, VolSync will spin up a new mover pod in the same namespace as your application. And this mover pod needs to be able to read and write to the PVC. If your application writes files as a specific user, in my case you can see user ID 568, well, the mover pod needs to be able to run with the permissions required to read and write to those files. And this is controlled via the run as user, run as group, and fs group fields right here. If you get this wrong, the mover pod spins up, sure, but it won't be able to read or write data, and your backups will contain nothing. Ask me how I know. Putting it all together, the full chain of events that triggers when a backup runs is as follows. Step 1, the trigger or the cron schedule right here fires. This tells VolSync to pick up the replication source and start a sync cycle. Then the step 2 would be the point-in-time copy based on the copy method you have configured. Again, for snapshot and clone it will create a point-in-time copy, but for direct copying it won't do that. In my case, for the snapshot mode, VolSync will tell my CSI driver to take a volume snapshot and then provision a temporary PVC from that snapshot. The application keeps running completely unaware of anything happening. Then VolSync will spin up a mover pod. It creates an ephemeral pod in the same namespace as the application, and this pod mounts the temporary snapshot volume and has the Restic repository credentials from the secret injected. Then it essentially just runs Restic backup. The first backup sends a full copy, but every subsequent one is incremental. You only send the delta. Because Restic handles deduplication at the block level, only the data that actually changed since the last backup gets transferred. Then, after the mover pod is terminated, the temporary PVC in the snapshot gets deleted, and finally the replication source updates with the status of the result. So for example, you can see right here in the status, my last sync duration was 47 seconds, the last sync time, the next sync time, the result for the last sync, as well as the logs from the pod. And also you can see when the repository was last pruned. That is the backup side. For the other side, the restoration, we have the replication destination. So if we go back into CRDs here and filter for VolSync again, let's take a look at the replication destinations, specifically at Jellyfin again. You can see right here that the replication destination defines what the restored PVC should look like. We have the storage access mode, the capacity, and also the storage class name. A lot of the fields here mirror the replication source we have on the left. We have the same Restic repository because obviously we want to backup and restore from the same place. We have the same cache configuration, but the key difference here is that the replication destination uses a manual trigger instead of the cron that is used on the source. The manual trigger works by setting a custom value here, and when the restore completes, if you scroll down here to the status, you can see that the last manual sync is set to the same value as the trigger right here. When a restore runs, the process is fairly similar. VolSync spins up a mover pod, it runs Restic restore to pull the data from S3 and then writes it into a newly provisioned PVC. A couple of other fields that are worth noting in this replication destination are the following. We have enable file deletion right here, and this is important because by default Restic restores are additive. If the destination volume already has files that aren't in the backup, they stay. Setting this to true, as I have right here, makes sure that the PVC always matches the backup exactly. Any files that are on the PVC get deleted and then we restore. Then I also enable cleanup of the cache PVC and the temporary PVC right here. And I tell VolSync to delete the temporary cache and working volumes after the restore completes to keep everything tidy. Additionally, you can see we also have the same mover security context right here, because again, if the application expects the files to be owned by a specific user, well, VolSync needs to run the mover pod, in this case to restore, as that specific user, so that the application now can read and write to those files. So, you've seen what the replication source and the replication destination look like when they're deployed in the cluster. Now, imagine writing all of that YAML, the replication source, the replication destination, the PVC, and the secret for the credentials for every single app. You saw I was using VolSync to back up over 20 applications, and that would be a lot of nearly identical YAML. This is where Kustomize components come in. If you've used Kustomize before, you're most likely familiar with the concept of overlays. You have your base set of manifests and then patch them or modify them as needed per environment. A component is a similar concept but slightly different. It's a reusable bundle of resources and or patches that can be mixed into any customization. In my repository, I have a components directory right at the root. Currently, it only has a couple of components, one for Dragonfly and one for VolSync. These are, generally speaking, to boilerplate duplicate code I'd need for apps if they require such services. The VolSync component, obviously, is the one we care about today. Inside components VolSync, you can see I have a customization.yaml that declares itself as a component. And then there are 4 resources. We have a replication source, a replication destination, the PVC, and then for the credentials, for the S3 endpoint and the encryption password and all that, I'm using an external secret to pull those values from one password. These are the same 4 resources we just looked at in the cluster, except that here, instead of being full of hard-coded values for Jellyfin, for example, they're full of substitution variables. That is where the Flux postBuild substitution comes in. In a Fluxtomization, you have this postBuild functionality, which essentially tells Flux after it runs Kustomize build to render the manifests to do a second pass through and replace all of these variable placeholders with the actual values you define. The clever bit right here is that this syntax supports defaults using this approach. Every manifest right here, you can see the replication destination, has sensible defaults. You can see the access mode is set to read-write once by default. The storage class defaults to my OpenEBS GFS storage class. You can see here the capacity defaults to 5 gigs, so on and so forth. Even the mover security context defaults to be using user ID and group ID 1000. That is because I try as much as possible to run all of the apps in my cluster securely, and that involves them not running as root. Typically, I try to force user 1000 wherever possible, and this just makes sure that VolSync runs the backups with the same UID as the app. The only thing that I must provide in all of these manifests is this app right here, because that is what drives the naming of every resource. You can see the PVC has the name of the app by default, the replication destination is app-dst, the replication source is also app, and finally, even the external secret is app-volsync. While we're talking about the external secret, let's take a look at it because it's interesting in my opinion. What I'm doing right here is that I'm templating a secret for the application from my Garage HomeOps Backups key secret in my 1Password vault. And you can see I'm extracting the access key, the secret key, the endpoint, the bucket, and the Restic password. What I'm doing with these extracted fields is that I'm using the templating engine right here to say the following. I want the secret access key to be the value of the secret key, access key ID to be access key, the password is set, and then for the Restic repository, I'm just building it manually by saying it's S3 column, then the endpoint / the bucket / VolSync / the name of the application. Basically, every app automatically gets its own prefix in the bucket. I have intentionally not used the namespace as part of this template because this is actually a quick and easy way to move an application between namespaces. I just back it up, nuke it, deploy it in the new namespace, and then just restore. I also want to separate all of my VolSync backups into a dedicated folder right here, and that is because I eventually also want to backup my CNPG clusters and other data into this bucket as well. So, what does it look like to actually use this? Let's take a look at the Jellyfin Fluxtomization, and that is in my media namespace, in Jellyfin, and it's this app.ks right here. You can see it's the standard Fluxtomization stuff, but here it has this components part, which references the VolSync component. Then I need to set the postBuild variables. Generally, I set this app variable to be a YAML anchor matching the Fluxtomization name. Then, for the VolSync capacity, I bumped my Jellyfin PVC to 10 gigs, and then I'm also setting the UID and group ID to 568. And that's about it. You can see that this Fluxtomization now depends on VolSync running in the storage system and on my 1Password Connect deployment in the security system namespace. This ensures that the operator is running and that the secret store is available before Flux tries to create the replication source and the external secret and all of that. Without this, you'd get a wave of errors on a fresh cluster bootstrap while things come up in the wrong order. Eventual consistency would kick in eventually, but enforcing this dependency just makes it all a bit cleaner. There is one more problem here that isn't obvious until you have enough apps using it. You see, all of my replication sources, if we take a look at the component again, they are all referencing the same cron schedule. Every 2 hours on the hour, at the top of the hour, every single application tries to snapshot, spin up a mover pod, and then push to S3 at the same time. On a single node, or even on a multi-node cluster for that matter, this might be enough to just hammer the disk, saturate the network, overload the NAS, or all three of those. I could just provide like a custom cron syntax here for every application with another variable, for example, but that gets annoying and tedious over time. The fix for this is something that I actually stole from OneDrop's HomeOps repository, another member of the Kubernetes at Home community, and it's delightfully janky. It's a mutating admission policy, but this is still a beta Kubernetes API, so I had to go into my Talos config here, into patches, and then enable it with these extra flags. Now, what is this mutating admission policy? Well, if we go into my apps, into storage system right here, into VolSync app, and then we take a look at the mutating admission policy, you can see it's a mutating admission policy binding, which I'm calling VolSync mover jitter, and it binds this policy. You can see that this policy looks for job resources in the batch v1 API group and version, and it looks for create or update operations. If the job has the VolSync job name prefix, so if the object metadata name starts with VolSync src, and if it has the VolSync created by labels, because when VolSync creates a new job, it sets up the ownership labels, this app Kubernetes IO created by. Then it runs this JSON patch on the job, and what this patch does is that it adds an init container running a busybox image. And basically what it does is that it generates a random number between 0 and 30 and sleeps for that amount of time. It's the dumbest possible solution to the thundering herd problem, and it actually works perfectly. The backups all still trigger on the schedule, but they naturally stagger themselves across a 30-second window instead of all of them hitting at once. So the GitOps side is fully automated. Backups run on a schedule and restores happen automatically on deployment. Cool, but sometimes you need to interact with VolSync manually. Maybe you're about to do something risky and want a fresh backup first. Or maybe you just want to check what snapshots are available before nuking something. For that, I have a set of Taskfile tasks that wrap the common operations. The way I have this structured in my repository is in two layers. In my Taskfiles directory, I have this volsync.yaml where I define all of the tasks themselves. The Taskfile layer here is intentionally minimal. It's basically just a CLI wrapper. It defines the required and then the optional parameters, and also runs some preconditions such as checking that the resources exist before trying to operate on them. Then it just calls out to the appropriate shell script. The actual logic lives in this .scripts directory right here in dedicated bash files. The reason for this split is that the Taskfile layer gives me a nice interface. I have named tasks, I have parameter validation, and I get descriptive error messages when preconditions fail. But I don't think that YAML is a nice place to write complex logic. I hate inlining multi-line bash within YAML, so the Taskfile just handles the are we good to go part, and the dedicated shell scripts handle the actual logic. Let me walk through the 4 tasks that I have. The first one is snapshots. This one lists all of the available VolSync snapshots for a given app. In this case, the app is a required parameter that I have to provide for this application, while the namespace is optional. If I set it, it will use that, but if I don't set it, it will just default to the currently active namespace I have in my kubeconfig. As a precondition, it checks for the app VolSync secret that contains the Restic repository configuration, and if everything is fine, runs the volsync snapshots.sh script, which we can see right here. What this one does is that it uses kubectl run to spin up a container that runs the Restic image, and then within that image, I just run Restic snapshots. To authenticate against the S3 endpoint, I'm mounting the environment variables from the VolSync secret that has the repository configuration. Then, once the pod is up, I'm just polling every 2 seconds for the pod to finish. If the phase is succeeded, then I just continue, but if the phase is failed, well, I just print the error and delete the pod. If everything went fine, I just print the logs, so that would be the actual snapshots in the repository, and finally I do some cleanup. Now, what does this look like? Well, if I use kubectl switch right here to go into my media namespace, then I can use task VolSync snapshots to list all of the snapshots for my Jellyfin application. This, if you look on the right, will spin up the VolSync snapshots Jellyfin container that runs Restic snapshots, prints the logs here, and then it cleaned up after itself. And these are the 28 snapshots available for my Jellyfin application in the Restic repository. Let's take a look at the backup task. Similarly, it checks for the secret to be present, but additionally it also checks for a replication source, because without it there's nothing I can backup. How this is used we can see in the backup script. What this script does is that it patches the replication source and it sets spec.trigger.manual to be the trigger value we saw earlier, so this backup now and then the timestamp. What this does is that we'll tell VolSync to trigger a new backup, and then I can just keep on polling every 5 seconds on the status.lastManualSync for the replication source. Once the last manual sync matches the trigger, I know that VolSync finished with the backup. And then I can just get the status of the last mover and then the result, and if that result is not successful, I can print the error logs. So, what does this look like then? Well, I can reuse the same command from earlier and then just use VolSync backup. This, if you look on the right, you can see it patched the replication source. This told VolSync to spin up a new mover pod. I am now waiting, and since the sync is in progress, and this is due to that MutatingAdmissionPolicy. You can see I am currently waiting for that jitter, which is supposed to help with the thundering herd problem. Once the jitter is done, the mover pod will start spinning up. And we can see right here, the result went into successful. If we look at the logs on the right, we can see again the 28 snapshots we saw earlier, but then we have an extra snapshot that was created right now, and the Restic snapshot was completed in 4 seconds. Next up, we have the backup all task, which I'm not gonna go into. I think you can guess what it does. It detects all of the replication sources in my cluster or in my namespace if I set one, and then it just triggers the same backup functionality on all of them. Finally, the interesting one is the restore task. This one checks for the secret and the replication destination, and finally calls the VolSync restore script. This one is a bit more involved since I can't really restore into a running application. So what I'm doing here is that I'm first suspending the Helm release to make sure that Flux won't try to go in and fix what I'm trying to change right now. Then I'm scaling down the deployment for the application and waiting for those deployments to be scaled down. Next, I'm patching the replication destination again with the trigger manual approach as we did earlier. I'm checking for the replication destination status to match the trigger. And finally, I'm also checking for the result here. If it's not successful, I'm printing the errors, but if it is successful, I am just resuming the Helm release and force triggering a reconciliation to make sure that the deployments are spinning back up. What does this look like then? Well, I can try again to run the VolSync restore task this time. And this patches the replication destination. You can see it spanned down my Jellyfin pods, and I now have the VolSync DST job that runs the restore. If you look at the logs, it uses the restore option --delete because I have that flag to delete files in the snapshot. And now it's pulling the data from S3, and it completed in 15 seconds, restoring about 11,000 files. Now, what happens next, you can see I'm resuming the Helm release, and I'm triggering a forced reconciliation. This makes sure that Jellyfin is now spinning up with the restored data. Alright, let's put all of this to the test. I've got here a simple Alpine deployment that's using the app template Helm chart. If you're not using this Helm chart by now, you're most likely missing out. This is the chart that I have been using lately to deploy almost everything in my cluster. Anyway, this Helm release just sets up a basic Alpine deployment, single replica, running the latest Alpine image, sleeping for infinity as soon as it wakes up, and just mounting a persistent volume at /data. The UID and group ID reinforcement right here is important because it ties directly into how VolSync does the backups thanks to the mover security context. If you look back in the VolSync component at the replication destination, for example, you can see in the mover security context here, the UID and group ID all default to 1000. So in this case, since Alpine is, let's say, standard and I'm able to use 1000, I don't even have to change anything here. Now, let me show you the Flux optimization for this Alpine deployment. You can see it's pretty standard stuff by now. It points to the app manifests right here, then it uses the VolSync component, and it sets the postBuild substitute variables. Nothing fancy here. In order to deploy this application, I can just push the changes to the repository and then trigger a manual Flux reconciliation so that we don't have to wait around for it. Now, in my K9S right here, on the right side, I'm watching all of the Flux optimizations, and you can see the Alpine Flux optimization showing up, and on the left side, I have all of the namespaces. You can see that the Flux optimization is waiting for VolSync since it needs the controller to be up and running, but now what's happening is that the VolSync DST container showed up. This means that the replication destination was generated, VolSync saw it, it triggered the restore, but as you can see here, no eligible snapshots were found. So this is the expected first run behavior. VolSync sees the replication destination, runs the restore, notices there's nothing to restore from, and then the PVC just starts empty. Now, let's give VolSync something to work with. So on this side, if I exec into the container, I can just cd into /data, and then I can just output some content into a file. In this case, I can say that this data survived a namespace migration. If we can read this, VolSync worked. If you do an ls now, we can see the file, and if we cat it, here is our content. With the data in place, let's go ahead and back it up. And I will do that using the VolSync backup task. If I just exit here on the left to see what's happening in a namespace, when I run this task, again, what will happen is that a new pod will spin up to do the backup. VolSync SRC will do the jitter wait initially for that thundering herd problem. Then, once that initial wait is done, the Restic container will actually spin up and start backing up our data. If we look at the logs now, you can see that there is nothing in the repo currently, but VolSync pushed a backup where it pushed one new file to the repository, and here we can see all of the snapshots in that repository. To validate that everything worked, we can run the VolSync snapshot task here, and this will just list again everything running in that repository, or everything that is currently backed up in that repository. And we can see that there is one snapshot to the timestamp of just about now. Let's break things. If we go back into VS Code here, what I want to do is that I want to go back into the namespaces or in the apps directory, and I will change demo A to demo B. Then I will do Ctrl-Shift-H, change all demo A to demo B, and if I push this to the cluster, what should happen is that Flux will try to delete everything from demo A, so that would be including the PVC, and then try to deploy again in demo B. Since these at the Git level are two individual changes, just deleting demo A and then creating demo B, I will actually do them step by step. So first, I will push the removal of demo A, then do a git push, and again trigger a Flux reconciliation. If I go back into K9S, if I look on the left here, we should see that all of the resources are in the terminating state, and the namespace itself should also be terminating. At this point, the replication source, the destination, the PVC, everything is getting turned down. This is the point where, without VolSync, you would be in trouble. With the namespace being terminated, let's go back into VS Code and push the changes for demo B. Again, if I push and trigger a new Flux reconciliation here, go back into K9S, we see the demo B namespace, and we should see the resources starting to come up. You can see here the VolSync DST pod spins up, and this one will try to restore all of the data from the Restic repository. You can see the restore options including --delete here because I have that flag enabled, and then in /data it restored this Restic snapshot ID, it restored one file, and it completed in 3 seconds. Now, the Alpine application is up and running, and what I can do to validate the data is there, I can exec into it, I can cd into /data, if I do an ls there is proof.txt, and if I cat that, you can see that the data is still there. I didn't run a restore command manually, I didn't trigger anything manually. I mean, I did trigger the backup manually, but that would run on a schedule anyway. And I did trigger the Flux reconciliations, but that's so we don't have to wait for them. Anyway, you get the idea. I deleted an app from one namespace, deployed it to another namespace, and the data followed on its own. Flux handled the state, and VolSync handled the data. That is the whole point of this setup. Your persistent data isn't tied to a namespace, a node, or a specific PVC. It isn't even tied to a specific cluster for that matter. It lives in S3. Wherever the component goes, the data follows. And that's VolSync. Once the component is set up, adding backups to a new application is just a few lines changed in a Fluxtomization, and then backups happen on a schedule with restores happening automatically on the next deploy. It's one of those things that you set up once and then kind of forget about it, which in my opinion is exactly what you want from a backup system. I do want to give credit where it's due though. The customized component pattern for VolSync isn't something I came up with on my own or at all for that matter. It's something that the Kubernetes at Home community iterated towards over time. If you're not plugged into that community, well, I'd highly recommend checking it out. There's a lot of really smart people in there sharing their setups, and this is a great example of what comes out of that kind of open collaboration. If you want to see how the garage bucket that VolSync pushes the backups to gets replicated offsite as part of my 3-to-1 strategy, well, I have that covered in my TrueNAS backups video. And if you missed the FluxCD video where I walk you through the GitOps setup that makes all of this work, well, there's a link for that as well. As always, my repository is public and linked in the description if you want to dig through the component, the task files, the deployments, or anything else. Thanks so much for watching, and as always, I'll see you in the next one. Cheers everyone.